Okay, section 6.6, the last section that we're going to cover in this course. It's probably the most demanding as far as how things are set up and different ways of finding the mean and the standard deviation. So, that being said, here's the deal. I've got this labeled as a histogram. In actuality, it's just a bar graph, but a histogram is nothing more than a special bar graph where the space between the ending point and the beginning point is minimized. They're close together, but the idea is exactly the same. In a histogram or a bar graph, we're concerned with just whole numbers. All right, so what we're going to do is use this bell curve from the normal distribution to approximate the answer we would get if we were doing a binomial problem that deals with whole numbers. So you say to yourself, hey, we're going to approximate something that we already know how to do. Doesn't make much sense. And you think, why are they even doing this? Well, they guess they want to. My only answer to this is that they wanted to finish chapter 6 off with a normal distribution types of problems. And quite honestly, you know how to do something. Now you're using another method to approximate something already know how to do. All right, it is what it is, our last section, so we'll just deal with it. As we know, when numbers are discrete, they're whole numbers, all right? And I say whole numbers versus counting numbers because I'm including the zero, all right? Zero is not a counting number, it's part of the whole number set. And when we work with the normal distribution, that bell curve, we're working with values that could contain decimals, right? Continuous values. So we have to make some adjustments. We're using this to approximate something that simply deals with whole numbers. So things are going to change. All right, we already know that N stands for number of trials, R the number of successes, even though in your calculator the R is replaced with an X, and for some reason the calculator TI doesn't understand R. Probability, well, that's P. We haven't dealt with Q in a long time. If you know the probability of something is, let's say, zero point 0.8, then you know Q is 1 minus 0.8, 0.2. As far as n times the probability being greater than 5 or n times the complement q being greater than 5, don't sweat this. This will always be in effect. I'm not going to give you a problem and say, oh, no, you couldn't do it because n times p wasn't. No, I'm not going to. That's nickel dime. What does change, though, is in prior problems, in prior sections, he always gave you the mu. He told you what it is. Here, you're going to have to calculate it. Mu is going to be n times p. Now, in many cases, you can figure this out because the values are so small, you can multiply yourself. But if the values get crazy, if we don't want to do the multiplication, just in your calculator, when it says, hey, what's mu, put in the n value times the p value, and the calculator will calculate it. Now, here, you're not going to do this on your own because the standard deviation in the prior section in 6.5, we knew we took the original standard deviation, we divided by the square root of n. And prior to that, in 6.3 and 6.2, he just flat out gave us the standard deviation. Here, you're going to have to let your calculator. Here, you don't want to do this by yourself off to the side. In your calculator, when it prompts you for standard deviation, you're going to use the square root key. You're going to say, hey, n, the square root of n times p times q. You'll know n, you'll know p, and then you can figure out what q is because you'll take 1, subtract p, and you'll know q. So this is different. These are the things that are different here, right here. All right. Well, actually, there's a couple more things, and we'll find out in a minute. This is the most challenging of all the sections. So there it is. There's how I find mu. This is how I find standard deviation, but your calculator will do this for you. You'll know all the values. Maybe not, you won't know the q, but you can figure it out. Key concept, we present a method of using a normal distribution, which is that bell curve, to approximate the binomial probability, which we did back in section 5.2. The conditions will always be met. N times p will be greater than 5. N times q are both going to be satisfied. I wouldn't sweat that. All right. Aside from figuring out these two values a little differently, there's a major thing you've got to do here. All right. Because the binomial only uses whole numbers and the normal approximation is continuous, we're going to have to do something called continuity correction, which simply means we're going to take the x value, subtract 5/10, and then take the x value and add 5/10. All right, what we're actually doing is finding class boundaries. Whole numbers are not going to exist. We're going to have this x value minus 5/10 and the x value plus 5/10, and then we'll have to figure out, hey, am I going to the left? Am I going to the right? And so forth. This is the sticking point here that you're going to have to get good at. All right, so here's as I said it, well, as is labeled here, continuity correction uses class boundaries. We're taking 42, subtracting 5/10, 41, 5, taking 42 and adding 5/10. 42, this whole number, if you're putting in a lower limit or upper limit of a whole number, you're doing it incorrectly. You're going to be using these decimals. So the first thing I do is, well, I'll show you in a moment, is subtract and add 5/10 from what it is I'm trying to find. And the reason we do that, Al did a nice job of explaining this. He said, hey, what if I'm interested in the probability that x is greater than 8? Well, if I have the histogram, no big deal, all right? But now I'm overlaying this normal distribution, this bell curve. Now, greater than 8, well, here's 8 right here. Greater than 8 would be from this red line to infinity. But if I look at this, the area of this rectangle here, if I start at 8, I'm not including all of this area here. So as Al said in the video, I got to start at 7.5. So 8 in all essence doesn't even exist. What does exist is 7.5 and 8.5. Now, greater than 8, well, in actuality, I should have said greater than or equal to 8, because greater than or equal to 8 includes 8. All right, it should have been a greater than or equal sign. All right, my bad. Greater than or equal to 8 includes 8. So I need to start at 7.5 so I can include the 8. If I start here, I'm missing all of this area that needs to be included. All right, so here's some examples. At least 8 includes 8 and above, so I'm starting at 7.5. Notice I'm not starting at 8. I'm not starting at 8.5. If I started at 8.5, I wouldn't include 8. All right, so it's 7.5 to the right. More than 8 doesn't include 8, so I'm not starting at 7.5. I got to start at 8.5. 8 does not factor into this. All right, more than doesn't include 8, so I got to start at 8.5. Now, sometimes you overthink these problems. At most 8 includes 8 and below. All right, includes 8 and below. All right, so I took the 8. I would have drawn it right here. All right, I wouldn't even put it on this horizontal line. You'll see in the videos I did in the previous section. I just draw something and put an 8. I don't put it here. So I subtract 5/10 and I add 5/10. Well, at most 8 includes 8. So I know I'm going to the left, all right, because I'm not going to 9 and 10 and 11. If I started at 7.5 and went to my left, well, I wouldn't include the 8 that's right here, so I have to start at 8.5. And sometimes people go, well, you say it at most 8, then why are you starting at 8.5? Well, you're doing it because of this continuity correction. All right, even though this says at most 8, I got to start at 8.5. If I start at 7.5, I would not include 8. So don't get all bent out of shape with that. All right, fewer than 8 does not include 8. That's why I'm starting at 7.5 and going to my left. If I started at 8.5 right here, I would have included the 8. Exactly 8, these are the easiest ones. Exactly 8 would be between 7.5 and 8.5. Those are the straightforward ones. All right, so here we are again, normal approximation to the binomial. Here we go. We are subtracting 5/10 and adding 5/10. These are my boundaries, and I got to figure out which way am I going. Am I including that number or not including a number? It gives you an example here. This is a kind of a strange one. Between 6 and 10. Well, to include 6 and to include 10, because it's less than or equal to, I got to start at 5.5, and then I got to end at 10.5. All right, to include the 6 and to include the 10. The video, he did a nice job with doing this with the video. All right, so what's changed? This will always be enforced. Don't worry about the product of n times the probability being bigger than 5 or n times 2. This will be a given. What's changed is, other than this continuity correction, you've got to, or the calculator has to, calculate mu, which was given to you in prior sections. And this is the one. Do not do this on your own. I think in the video, Al actually came up with a decimal. No, because it's going to be a rounding error. All right. In where it says, it's going to ask you for, excuse me, a left bound, a right bound, like it did before, a mean and a standard deviation. When it comes to standard deviation, you're going to put in the square root, pop in the end, the p and the q, and the calculator will do it for you. Do not do this on your own, because a lot of times it's some crazy decimal. Let the calculator do all the work. That's what it's there for. All right, once again, he's talking about drawing a vertical strip that represents the value in question. Subtract 5/10 and the value in question plus 5/10. He's talking about here, shading in the area to the left or the right, depending on which way you're going. Does it include the value that I'm interested in? Does it not include? Now, I did these. I did a video, and I actually drew it, the curves. Some of the curves look pretty, at least something to be desired, but, I'm not an artist. But anyways, I did these. All right, so you should have an idea from the previous homework, which was last Thursday for most of you. Last Thursday's homework. This is going to be next Tuesday or next Thursday, depending what class you're in. My voice must be. All right, so there I'm doing it again. There's the video link, but you should have watched this already, where I did my best job, my best effort to draw a bell curve. All right. This falls into the category of a binomial experiment, but we're going to use the normal distribution to approximate this. Now, you got to say to yourself, if I'm going to use this normal to approximate something I already know, maybe I could use binomial PDF or maybe binomial CDF. Just a thought. You could, do it the way you did it back in 5.2 and then find the closest answer, because you're trying to find an approximation. You're actually going to be finding the exact value using a binomial PDF and binomial CDF. Just a thought. Just a thought. You can go back and do it another way and get an answer. Now, whether the approximation is close to that answer, well, that's to be determined. I may talk about this a little further, but just putting that bug in your ear. You already know how to find the exact answer. Here we're trying to find an approximation of something you already know. That makes sense. I don't know why that slide is there. I must have hit previous. All right, so we're trying to find probability of R being greater than 280, which is 281, 282. If I was doing this back in chapter 5, I would have used the cumulative. I don't know why I'm coughing. I would have used the binomial cumulative, where it starts at 0. I would tell it to stop at 280, and then I would subtract that answer from 1, and that would give me from 281 all the way to 300. That was what we did in 5.2. All right, so what are we doing here in 6.6? All right, I put the mean in. Sometimes that confuses the situation. I don't really need it because I know this is the mean right here. So there's my 280. Now notice, 280 does not, for all intents and purposes, exist. If you're using a lower limit or an upper limit of 280 or any whole number, you are doing it incorrectly. All right, so I figured out what mu was. I took the 300, I multiplied it by the probability of a success, which was 0.85. All right, and the calculator could have done this. Where it says mu, I would have put 300 times 85. It would have figured this out. There's no need of me doing this off to the side, pencil and paper. There's E99 to the right. All right, so greater than 280. Well, greater than 280 does not include 280. So greater than means I'm getting big. I'm going to my right. I know that. But if I started here at 279 and I went to my right, I would have gone right over 280. I don't want that. I don't want to include. It says greater than. I need to start at 280.5. Worst case scenario, you start at 280. It does not exist. You've got to subtract and add 5/10 to find out, hey, these two boundary points. All right, continuity correction. Greater than 280 would be from 280.5 all the way to the right. So this would be my lower bound. This would be my upper bound. All right, notice here. All right, so I'm starting at 280.5. My lower bound is my upper E99. Notice I didn't figure this out. I didn't have to do this, but the 255. I could have, but the calculator will take the n value 300 right here, n equals 300 times the probability of a success 0.85. Heaven forbid I do this on my own. Let the calculator do it. Standard deviation, the square root of n times p. Well, if p is 0.85, then obviously q is 1 minus 0.85, 0.15. That's not a big deal here. Not a big deal. All right, and I come up with this answer. Now, what does this mean? This E stands for the number 10, 10 to the negative 5, which means I'm going to take the decimal point and I'm going to move it 5 places to the left. So you see you'd have, on an answer sheet, you'd have 4 zeros followed by a 187. E to the negative 5 means take the decimal point, move it, because it's negative here, you're moving it 5 places to the left, which means you'd have a decimal point, 4 zeros, and then a 187, depending on how many decimal places were required. All right. It's estimated that 3.5% of the general population live past their 90th birthday. Oh, I know that because I have a mother and a mother-in-law both over 90. All right, in a graduating class of 753 people, what's the probability? 15 or more. Well, 15 or more includes 15. All right, so includes 15. Now, more means I'm moving to the right. To include 15, I'd have to start at 14.5. I'm not starting at 15 because 15 doesn't exist. Whole numbers don't exist in this continuous binomial distribution. All right, what does exist is 14.5 and 15.5. Well, if I start at 15.5 and go to the right, I'm not including 15. Notice he says 15 is good or more than 15. So I'm starting at 14.5. I'm going all the way to positive infinity. Mu is equal to n times p. Well, there's my n value, right? There's 750 high school seniors, and the probability that one of these people in high school live to be in their 90s is 0.35%. Now you got to remember that 3.5% expressed as a decimal is 0.035. I'm moving that 0.2 places to change a percentage to a decimal. You're dividing by 100, which indicates, which means you can only move the 0.2 places to the left. That's 0.35. Sigma is n times p. Now, I could take 1 and subtract 3.5%. What would that give me? 96.5%. Or you could do this. You could say, there's my n, there's my p, times my q value. If you didn't want to calculate what q was, you could tell it to calculate, hey, take 1, subtract 0.035, all right, which is in essence, 96.5%, which is 0.965. But I'm saying if you didn't want to do that. Now, you can't see it here because the screenshot doesn't give all of it, but there's ways of letting the calculator do the work for you. That's what it was meant to do. All right, so there's the answer. Now, if you're looking between 25 and 35, I said in the previous video, chances I won't give you one like this. I'm starting at 24.5, going all the way to 35.5, so I can include the 25 and 35. There's the mean, and there's the standard deviation. It's the same way it was done here. N times P times Q. Q could be 1 minus this if you didn't want to calculate it. I definitely wouldn't want to find the mean on my own. Let the calculator do this stuff for you. Why find that out? Waste time to put a decimal in when the calculator can do it all by itself. It doesn't need your help. All right, so there's the answer. Now what I've done here, I've done these the old-fashioned way using tables and the like. So all I did this for is that if you're doing the other two here, you can find the answers and see if you did it right. But I'd be cautious. 30 or more, I have to start at 29.5, go all the way to infinity. More than 40, well, more than 40 would not include 40. So I would draw my curve. I would put 40, but I wouldn't have it on the horizontal axis. I just have it in the body of that bell curve. I would subtract 5/10, 39.5, add 5/10, 40.5, and then I would figure out which way am I going. More means getting bigger. Now, the second question I asked myself, am I starting at 39.5 or 40.5? Well, if I start at 39.5 and go to my right, I would go right over the 40. I don't want to include the 40 because it says more than 40. So I'd have to start at 40.5, go all the way to positive infinity. All right, so there's the answers to some of those. And here again, I would caution you. Well, these are all right. Yeah, more than. Sometimes they flip the script on you. And those are the answers. This is what I'm talking about. These two here don't talk about failing. They talk about succeeding. It gives me the probability of failing, which is 80%. So these two were, if the probability of failing is 80% on these two, you'd have to use 0.20 because you're looking for success. But I didn't want to make it tougher than it had to be. But if you're doing these two and the answer's not coming out right in the next slide, it's because here is succeed, here is succeed, and here he's giving us the probability of a failure. All right, so that would affect the way that you calculate mu. Mu would be n times p, and these two p would be equal to 0.20, and these two p is, just as they say, 0.80. All right, there it is. So fewer, 58 or fewer. Now notice, 58 or fewer includes 58. Fewer means I'm going to my left. Well, I wouldn't want to start at 57.5 because that would include 58. 58 is good. It's allowable. So I have to start. Here's another one here. You know, you see you're starting at 58.5, and then you read it. You say, well, 58 or fewer. Don't get too. If you've drawn your 5/10 subtracting and adding, and you know whether it includes it, don't get too crazy trying to say, well, 58.5. He says here 58 or fewer. No, this is correct. I gotta start at 58.5 because if I go to my left, I gotta include 58. If I started at 47.5, went to my left, I would include 58. So don't try to second guess yourself. All right, that this doesn't meet that. This is correct. You know you got the right answer, and you're going all the way to negative infinity. You're going to the left. Mu is n times p. Standard deviation is n times p times q. Well, obviously, if if p is 0.80, then q, the complement must be 0.20. That's no big deal. That's no big deal. The calculator will do everything. And there's the answer to that one. And there's the answer to all A, B, and C, and D. To be truthful, the section 6.6 practice worksheet contains a lot of examples. It's 20 examples. And I may spread that out over a couple of days because we find ourselves in a good spot here as far as the time that's left and what we have to cover. Basically, we're only covering this one more section. I'll be doing a voiceover, or I just did a voiceover of the PowerPoint. Next thing is I'll assign the 1 through 20, the 6.6 worksheet, and then I will produce a video that goes through all these solutions to the 6.6. And that's still going to give us a couple of days, all right, especially the class in Bridgewater. And what I want to do is I'm not going to, I find myself in a situation I don't want to go to chapter 7. So you catch a break because you'll have a couple of extra days to study this and maybe work on your optional extra credit if you're doing it. And if not, you're going to have a couple of free days here to prepare for your other finals. I've been blown away by the results that I'm getting. It's almost like I do a better job of teaching this stuff when I'm here on my couch. And you do a better job of answering the questions when you're on your couch. So go figure. Anyways, be safe, you and your family, and I'll catch you on the other side. Thanks.